Hello, welcome to Regression diagnostics in Stata. This video covers the second part of homoskedasticity assumption about the linear regression. And this video talks about when we don't have this assumption being met, meaning that we have heteroskedasticity issue, and that has to be solved. And that means that we have the model predicting some values of y better than others. And however, this does not mean that OLS is biased. OLS continue to be consistent. However, we have some consequences. If this happens, we will have biased standard errors. We will have standard errors that are underestimated. We should have higher standard errors, but the model will give us lower standard errors, and that will lead to wrong conclusions. So heteroskedasticity increases the variance of the coefficient ideally. So we should have higher p-value, and that should lead to we rejecting keeping the null hypothesis. However, the OLS procedure does not detect the increased variance, okay? So if a OLS does not detect the increased variance, it's going to affect the computation of the t-values and as well as the p-value. So in the end, we have underestimated standard errors, and that gives us lower p-values. Because when we divide the coefficient value by the standard error, then we are supposed to get the t-value. And that also shows what kind of p-value we should have. Okay, so that leads to biased inference, and meaning the OLS is no more blue. And OLS is inefficient. It is not utilizing all the observation well. Therefore, we cannot generalize the result from the population, from the sample to the population, and therefore invalid hypothesis testing. Okay, what do we do when we have a problem like this? We use what we call the heteroskedasticity consistent standard errors. And the second approach is to transform all our variables that may be not be far from normal distribution. And we can use log transformation, and we can also Winsorize all variables. What it means is that to train both ends of the data set, whether small and then the bigger values. Now, when we use the robust standard errors, we have more better accurate standard errors. So standard errors will change from the original result. The t-statistic will also change and give a more accurate value, and the p-value will also change, which is more accurate. But the coefficient remain the same. Take note. We continue to use the automobile data set, and we will test how to control for heteroskedasticity problem. The only thing we do different is to add a command there to the command, comma, we have the robust. We just add robust components to the regression model or specification. So let's do that in Stata right now. So open Stata with me, and then we will load the same data set that we used in the previous video. So just type system use to get the data loaded. Let's see when that is done. Yes, we have the data. Now let us run the regression model without the robust standard error to see what kind of result we will get. Okay. So here we have the coefficients for all the variables, and we see that with the exception of MPG, the rest are significant. This could lead to wrong conclusion because we have heteroskedasticity problem, and we have to control for that by using the robust. Notice that the coefficient values are supposed to be the same, but standard error is supposed to change, t-values are supposed to change, and then p-values are supposed to also change. Let's do that and see. So here we just add robust to the same command for specification, and let's see the result. So now we see that before we have the coefficient being minus 1, 3, 1 minus 1, 3, the same. But then you see that the standard error is now 72, here is 75. The t-value here is minus 0.119, minus 0.18. And you see the p-value also changed marginally. And we see noticeably that the length as a variable is no longer significant at the 95% confidence level. So we see that here it was significant, but it's no longer significant. So without controlling for heteroskedasticity problem, we can make wrong conclusions. We could have said that length is significant when it is not, when we control for robust, when we include the robust. Okay, so this is how we control for heteroskedasticity problem in Stata. And in the next video, we will cover autocorrelation, how to test for autocorrelation to ensure that we don't have autocorrelation problem in our data.